So welcome everyone. I want to talk today about occupancy grid maps, which is a representation of the environment that a lot of mobile robots use. So they use these types of map in order to represent the space around them and in order to do various of different tasks, such as planning a path towards a goal location. And these occupancy grid maps can be seen as kind of architectural floor plans. So what they do, they basically store information about which parts of the environment are occupied and which parts of the environment are free. And you can see this, for example, in a very similar way when you want to rent an apartment. The landlord typically sends you a floor plan, so you have an idea how the layout of the environment is. And what's written in this floor plan are typically the walls. So the walls are painted with black ink, for example, and white represents free space. And occupancy grid maps can be seen as very similar to that. They store in an image-based representation, or it looks like an image to us, the occupied and unoccupied areas in the environment. So wherever we have white pixels, we can see this as free space, and where we have dark or black pixels, this could be the occupied space. The difference may be that we do not only store walls, we may also store all other types of objects that are standing around in our environment. And this kind of gives you at least an intuitive idea on what an occupancy grid map is. And in this lecture today, we want to dive a little bit deeper, understand the mathematical model which sits behind those occupancy grid maps, and we'll discuss how we can derive such occupancy grid maps from real-world sensor data. So first of all, why should we care about maps? Maps are needed for a wide range of robotics applications. So whenever you have a system which should navigate through the environment, and it shouldn't do that in a random fashion, then robots often use some type of internal map representation. Those map representations are needed for tasks such as localization, so in order to determine where you are, given a map of the environment, or for planning a path. So if a robot is at a current location and wants to drive towards a target location, then the robot needs to have a map of the environment in order to plan an optimal or near optimal plan. You may just tell the robot, drive towards the target location. Maybe the system will be lucky and reach this target location, but if there's an obstacle in between, the system may get stuck. So planning approaches which rely on maps are a better idea if you want to have an effective navigation system. So the map represents the environment for the robot. So everything that the robot understands about the environment is typically stored in that map. And they tell us what the environment looks like. This can be occupancy information, so where is an obstacle, where is free space. This could be the location of distinct points in the environment, so-called features or landmarks, but this could also be something else. This could also be semantic information, just as what is actually there stored in the environment. But this depends on our application. For today, we will look into occupancy information, so which part of the environment is free and which part of the environment is occupied. And so the task of learning those maps from sensor data is a fundamental task in most robot navigation systems. Because even if you provide the robot beforehand with a map, the possibility that the environment changes or that something needs to be updated in the map is actually pretty high. So systems need to be able to, on the one hand side, determine if the map representation that they are using is still up to date, and if not, update the map of the environment. And this happens typically based on sensor data. So what types of sensors are we looking into? I've shown here a few popular sensors that you find on a lot of mobile robots. This can be monocular cameras, stereo cameras, or RGBD cameras, or maybe laser rangefinders in 2D or in 3D. And we will be looking here today into sensors which provide me proximity information. So this could be a laser range scanner, but this could also be a stereo camera or an RGBD camera, maybe not necessarily the monocular camera, although there are approaches today which try to estimate the depth information also from a monocular camera. So our assumption here today will be basically that we have a range sensor, and we do two small examples with that. One with a sonar range sensor, so something which is more a little bit outdated technology, let's say that way, at least on robots that are out there today, which typically use more high quality sensors, unless it's a very cheap device. So then the second example will be a laser scanner, something like this over here. So we will look into the question on how to build a map of the environment with such a laser scanner. So in general, we need to distinguish two types of map representations, so-called feature-based representation and volumetric map representations. So feature map representations basically store the location of distinct points in the environment. So there's an example here of Victoria Park in Sydney, where tree trunks could be or are one type of landmark that the system uses in order to estimate this landmark map, so a map of trees. And when they are, you can use then this map representation in order to localize in the environment. We are not looking into feature-based representations today. We will look into volumetric representations. This can be in 2D, this type of floor plan map that we see over here, or we could even extend it to 3D and then store a full volumetric model of the environment. And again, they are both different types of representations. We can use both, for example, for localizing a robot in the environment. Given that we here often want to plan a path through the environment, I feel that this occupancy grid-based representation are more suited because they explicitly represent free space, and we can use them in order to plan a path through the free space, and therefore they are preferable in several applications. So today we will be looking into these type of occupancy grid maps. How does a robot look like that could build such a map? So this is a simple example. It's one of the platforms that we have in the lab, a U-bot, which is equipped with two of these horizontally looking 2D laser rangefinders, these Hokuyu rangefinders, and they can drive through the environment. And a very simple occupancy grid map could look like this. So what you see here is basically an image rendered from such an occupancy grid maps. We see white space here in the middle, which represent the free space, and we see those black pixels, which represent occupied space. So basically locations in the environment where there was an obstacle. For example, here was a box standing in the environment, so you see the outline of that box represented in this map representation. And this is an example for a simple occupancy grid map. We can also build other types of representations. So this is a platform navigating through the catacombs of Rome, a platform that we had built together with other partners within a European project from Rome, Algorithmica, KU Leuven, and Aachen, and other cooperation partners that we had, with the goal of exploring catacombs or ancient structures. And for that, you need to build a 3D model of the environment. And so you can see here a part of the point cloud that the system was generating while navigating through these tunnel-like environments. This is also a map of the environment, a volumetric representation, although you may not call a point cloud really a 3D model, but we could use this 3D point cloud data in order to render, for example, also a 3D occupancy grid map out of that. This becomes also relevant for autonomous cars. So you have a vehicle, like this vehicle over here, which is equipped with cameras and laser range scanners here on top of the vehicle. We can actually drive around here on campus and then build a map of the environment. So this is a 3D representation of our parking lot here in the back, and you could see the vehicle which was driving around here and building that map from the 3D LiDAR data while navigating through the environment. We can do this completely just representing the geometric information as we have seen it over here, or we could also store semantic information, so also storing what we actually see. For example, what's a road, what's a different car, what are building structures here encoded in colors. And we can use this from the raw point cloud data, basically coloring every endpoint depending on the semantic class. And we can also turn this into a voxel map. So a voxel map, you can see this as an extension of this idea of this 2D floor plan into 3D, where you basically have not 2D elements, pixels, but you have voxels, so 3D elements, which represent a certain part of the 3D space, like a small cube, and tells if this cube in the world is occupied or not. This is kind of an extension of this idea of occupancy grid maps from 2D into 3D. And we want to look today into the underlying model that sits behind this occupancy grid maps, or voxel maps storing occupancy information. So if we think about the typical mapping task, then we typically want to estimate the map of the environment given my sensor data and my control commands. So give me the most likely map given the sensor data. And the sensor data can be camera data or my LiDAR data. And we're interested in providing the map or estimating the map that can be best explained through this sensor data. Today we go for a slightly different variant of that. We are looking into systems where we assume to know the pose of the platform. So we are not necessarily interested in the odometry commands here anymore. We are saying we kind of ignore that. We assume to know already the poses where the system was in the environment. This is encoded by going from u to the variable x here, which is given. So we want to estimate the map given our sensor data, our sensor readings, as well as the position of the platform in the environment. So it's a simplification of the in general simultaneous localization and mapping problem where we need to estimate where the platform is and build a map of the environment at the same time. So here we are only interested in estimating the map. We assume we already know where that platform is. Okay, so if you think about an outside environment, you maybe have a very good GPS IMU combination, which directly provides you at least with pose information, and then you can use this pose information in order to build a map of the environment. That would be one example for this mapping with known poses, at least if everything works well and we have a good GPS signal, and scale-wise this is still fine. Indoors we may use other techniques in order to estimate where the platform is, but for the lecture today we assume that to be given. So we are only interested in estimating this variable m. So what does the environment look like, ignoring the potential pose uncertainty that is involved in that process. So it's therefore also something that's called mapping with known poses. So for today we're looking just into maps that can be built with given this pose information. There are different ways to represent maps. I said that before. One is feature-based representation, where the map is basically just a list of points of these feature locations. That's something that we have seen, for example, in bundle adjustment, where we estimate a 3D model of the environment that consists of 3D points. This is a standard approach in computer vision or in photogrammetry, where we typically extract point features from images and try to estimate the location of these point features in the 3D space. And if we observe these features multiple times, we can basically reduce the uncertainty in the pose estimate of those landmark locations. So landmark map in the end would just be a list of points, typically stored their location and maybe their uncertainty. That would what a feature map would look like. And this is something which we don't want to look into today. We want to look into this idea of using a grid map, a discretization of the environment. So grid maps or occupancy grid maps discretize the environment and represent a variable for all the discretized space. And in our case, this is the occupancy information. So is a part of the environment occupied by an obstacle, yes or no? That's basically the question that we want to answer for all parts of the environment. And for that, grid maps discretize the environment into so-called cells, or occupancy grid cells in our example. You can see those cells as tiles on the floor. So if you have a floor made of tiles, and these are whatever, 30 by 30 centimeter tiles, you can see all of those tiles as one cell. And we store for every cell, is this tile occupied or free? And of course, not all the environments have those tiles. You can see them just as virtual tiles. So just put a uniform grid over the environment and store for every grid cell if it's occupied or not. And these grid cells can, if you think about an image, be seen as the pixel in an image, just kind of as a simplification for you for understanding that, because you probably have worked with images. So we use this grid, and this grid structure is typically rigid. And every grid cell, it's a uniform grid, represents a certain part of the environment, let's say a 5 by 5 centimeter area of the space. And we want to estimate for that area, is it free or occupied? And we want to do that not just for one cell, but for all the cells in the environment. And the occupancy grid maps typically make the assumption that a cell is either free or it is occupied. There's no other state than being free or occupied. Either there's an obstacle in there, then it's occupied, or there's no obstacle in there, then it is free. And they don't use any type of parametric representation of the environment. So it's not like in the feature space where you may use Gaussian distribution in order to represent the location of a feature. We just have this non-parametric representation, this grid structure where we store for every cell just is it free or occupied with a so-called binary random variable. What is an issue of those grid maps? They can get very large. So if especially if you think about 3D structures. If you don't do this only in 2D but in 3D, then the memory consumption can grow quite substantially. In 2D, it's probably still okay to store them as a map information. So this may be seen as a disadvantage, especially if you have very sparse space. Then a feature-based representation may be better, but they have other advantages, for example, that they don't rely on a specific feature detector that you would need if you build a feature map. So just go a little bit into an example. How does an occupancy grid map look like? So this is a map of an indoor environment. That's the building where I spent my PhD time at the University of Freiburg. These were different offices. I was sitting somewhere over here for a long time, and at part of time somewhere over here. And what the map here shows is the structure of the space, where everything every black pixel represents occupied space, and all the white pixels represent a free space. So if you kind of zoom in here into this kind of doorway, then we can see in the zoomed in view that they are cells which are black, which are here the walls, and also this part of the wall which is occupied, and the rest of the space is free space. You may see also some gray color over here. This is basically space we haven't seen, but we don't know if the space is occupied or free. But to that we will come in a second, how we can represent this. So we're talking about this type of representation. So the pixel structure basically gives me the grid structure, the discretization of the environment, and we want to store for every pixel, is this part of the environment free, or is it occupied by something? And occupancy grid maps make assumptions about the world. And the next thing we want to do, we want to look into those assumptions and then see how we can actually model this representation in a mathematical fashion. So let's start with the first assumption. Assumption number 1 tells me that the area which corresponds to one of those grid cells is either completely free or completely occupied. So there's only 2 states, free or occupied. There's no other state. So it doesn't mean that my model may be unable to tell me if it is occupied or free. That's not what I'm talking about. I'm talking about the assumption that every part in the environment, the physical space, either occupied or it is free. So if you show this in a very small, simple 4x4 grid structure, that would look like everything which is black over here is the occupied space, and whatever you see here in white is the free space. So an environment where we have here, let's say, a wall or an object and free space everywhere else. And again, the assumption is either fully occupied or it is fully free. That's again something which doesn't really hold in reality, because we can have objects which are smaller than my grid size. Or we can have the situation that this grid structure is not perfectly aligned with a wall, for example. If you have 45-degree rotated, so if you have a wall which is by 45-degree rotated with respect to the virtual grid structure that you put over the environment, you will have cells which are only partially occupied or partially free, because the wall passes through the middle of that cell. That's something that can happen. And so this assumption is, again, just an assumption. It's nothing that we can enforce in the environment. Okay, so it's something we assume, and we'll create a model based on this assumption. That was the first one. The second, so if we have that, what we can do with this assumption is that we can say every cell can be represented by a binary random variable. So a random variable which just has 2 states, occupied or free. And of course, when we are estimating the state of the environment there, then we can have numbers between 0 and 1 representing the probability for being occupied or being free. But the state itself, so the 2 possible states, can be represented with a binary random variable. So if we want to estimate the occupancy probability, that's where the name comes from, occupancy probability map, or occupancy grid in short. This is kind of P of Mi. Let's say this is a cell with the index I, then P of Mi, if it is 1, it means this cell is occupied. The probability for occupancy equals to 1. So it means I'm sure this cell is occupied. In this example, that cell Mj, be this one, has a probability which goes towards 0. That means I'm sure that this cell is free, because I know it's not occupied. So probably goes to 0, means not occupied. And that means free in our notation over here. And so for all of those cells, we need to store one binary random variable in order to represent the probability distribution about the individual cells being occupied or being free. Okay, so a binary random variable, let's just consider one cell here for the moment. It means a cell is definitely occupied, means P of mi equals to 1. If the cell is not occupied, it's P of mi equals 0. And if we don't know anything about it, we say, oh, actually we don't know, it's free or occupied, both happens with the same probability. Then we may represent this with 0.5. So we don't know anything about it, and the probability of my prior for being occupied or being free is identical. Then I could represent this with a probability of 0.5. And if I maybe gathered some information, but the information is noisy, and let's say I have a value of 0.8, I have an occupancy probability of 0.8, it means I'm more certain that the cell is occupied rather than it is free. So with 80% chance this cell is being occupied. This is what 0.8 would mean. Okay, in terms of the notation, just to be very clear about this, I use this small mi in the way I introduced it in the probability primer. This is a probability that the cell is occupied, the cell with the index I, so that this one takes the value of being occupied. If we write it down in a different mathematical form with the with the binary random variable and the random variables written here in capitalized letters, let's say P of mi being occupied, also sometimes written as P of oc, so the occupancy probability of that cell. But we typically use just this kind of short notation, but just to make sure you know what it means. And of course we have also the opposite event that a cell is free, so P of mi being free means P of mi being not occupied, also sometimes written in this form or with the negation, whatever form we are using, just to make sure we are all on the same plate here, knowing that what means occupancy probability. So cell being occupied and the opposite event of it being free. In terms of visualization, we typically visualize black pixels with cells being occupied, white pixels with cells being free, and grayish pixels with values where we don't exactly know if the cell is occupied or free. And the larger the probability, so the more the value tends towards 1, the darker the cell gets, and the more the probability goes towards 0, the brighter the cell gets. So we can, the color, the shading of the color tells us something how certain we are about the environment. So in this example, in this gray cell, it would be an occupancy probability of 75%. That means the probability of being free is 25%. So just kind of that you know the color coding of what I will be using here and what that actually means. And we have a second assumption that the occupancy grid map does. And this is a so-called static world assumption. That's something that a large number of mapping systems still do. They assume while we're recording the sensor data, the world doesn't change. Again, that's clearly an assumption. We cannot guarantee this. Our world is dynamic. Even if you have a robot building a map of the room, someone is walking through the room, walking through a laser scan, for example, then the world is not static anymore while being observed. Although most mapping systems and also the approach we are presenting here today makes the assumption that the world is static. So if you have something which is occupied, it means it will be occupied, will stay occupied forever. And if something is free, it will stay free forever. It doesn't mean that we maybe have contradicting sensor data due to the sensor noise that we have, that we say, oh, this cell is occupied, although in reality it is free. This can happen, but we know that in reality the state of each cell is either occupied or being free. That's the second assumption. And the third assumption that we have is that those cells are independent of each other. So there's no dependency between those cells. So if I know the occupancy probability or the occupancy of one cell, it doesn't help me to estimate how the neighboring cell looks like. Again, that's something we can argue if this assumption is valid or not. The reason why we're using it is because it dramatically simplifies my model. If you think about man-made environments, if you have a wall, for example, then if you have a cell which is occupied due to a wall, it's very likely that one of the neighboring cells is also occupied because our walls are typically large, have a certain extent. Same holds for objects that we place in the environment. If you put a table into an environment and we have a cell which is occupied in the middle of the table, it's more likely that the neighboring cells are actually also occupied rather than free. So the neighboring information can encode something, can tell me actually something. So this independence is not fully justified, but we use it as a simplifying assumption in here. Again, these are assumptions, these are things which do not hold in reality, but I assume them to be because it makes my model easier and computationally tractable. And that's the reason why I, as a designer of this algorithm, make those assumptions. Again, those assumptions are always points to revisit when your system breaks. So if your mapping system fails at some point, it's a very good idea to revisit your assumptions and see if one of the wrong assumptions that you have made may have caused the problem that you experience with your system. So it's always very good to know what your assumptions are. So in sum, we have these 3 assumptions. A cell is either fully occupied or fully free. The world is static. That means if something is free, it will be free forever. If something is occupied, it will be occupied forever. No one is moving through my space. No one is modifying the space. And the third assumption is that these individual cells are independent of each other. And this has a direct consequence, a direct impact on how I can model my environment. So we said we have a map that consists of cells, grid cells. So P of M refers to the whole map in general, and P of M in an index refers to an individual cell. Maybe we arrange them with an X and Y coordinate, but for reasons of simplicity, I just use one index here, which can index all the different cells in my environment. So what we have, if we want to talk about the occupancy map, it is a probability distribution representing the whole map of the environment, all the different states that we have. And if we want to represent this in general, it would be the joint belief. So the probability distribution about the map is the joint belief about the values of the individual cells. Okay, so this is represented by this fact over here. So it's the probability that the whole map is occupied is a probability that cell 1 is occupied, cell 2 is occupied, cell 3 is occupied, and so on and so forth. So the problem is I may have a very large number of those binary random variables in here. And what we want to do, we want to simplify this potentially very, very large joint probability distribution. And we do so by exploiting the assumption number 3 that the cells are independent of each other. If the cells are independent of each other, I can simplify this joint belief into a set of individual beliefs. That's again something on this, if you think about the independence that we have talked about in the probability primer, that's the point in time where we're using it. So if these variables are independent of each other, I can actually break them down in a product of individual probability distributions, just talking about one single cell. And this is something that you can see here. We can simplify the probability distribution over the map as a product of the probability distributions over the individual cells. And this is something, is a result of this independence assumption, of this assumption number 3. So assumption number 3 leads to this simplification over here, that we can actually write this down in this form. Okay, so let's look into a concrete example where we look maybe into 4 cells. So what you see here on that slide is a map consisting of 4 cells, and so P of M is a product of the individual cells. So if you want to ask the question, are all those 4 cells occupied? So which is kind of just for illustration purposes done in this form. It means, is the cell representing, the random variable representing cell number 1 occupied, times the probability that 2 is occupied, times the probability that 3 is occupied, times the probability that 4 is occupied. Okay? So in here I used kind of this M versus M in order to, so capital M versus small m, in order to distinguish the random variable from the value itself. So here I'm asking, what's the probability that all those cells are actually occupied? And I can directly take the occupancy probability values from my map and multiply them with each other. Maybe, however, I'm interested in a different map instance. So if I say, what's the probability that 2 of the cells are occupied, especially those 2 ones, and that those 2 are free? Then this would be the probability that M1 is occupied, that M2 is free, that M3 is occupied, that M4 is free, just the product of them. But since I don't store the probability of a cell being free in my map, only the probability of the cell is being occupied, I can now exploit the first assumption that a cell is either occupied or free, so it's a binary random variable, and can put M2 is free, means 1 minus PM is occupied. So I can turn this into the occupancy probability, just putting the minus 1 over here. And again here, so these are one of those situations where it helps to distinguish between the random variable itself and the instance that I'm actually interested in, for example, or a specific configuration over here. But the key thing is we have a map, and this map can be broken up into cells. Those cells are independent of each other, and so they turn into a product of individual small probability distributions, and they are binary random variables, so they can be either occupied or they can be free. So that what we want to do as the next thing is we want to estimate this type of map representation from data. So we have specified how our mathematical model looks like. It's a joint probability distribution which can be broken up into a product of individual probability distributions, and they can be represented with a binary random variable. That's what we exploited so far. And now we want to estimate this map from data. So given we have sensor data, Z1 to T, so sensor data recorded at different points in time, and we know the position of the platform, X1 to T, and we want to estimate the map. So we want to estimate the map of the environment given sensor data and position information. And I will be using here range sensors. So, but what we actually need is a sensor which tells me something about occupancy. So which tells me something about, is the cell I'm seeing free, is the cell that I'm seeing occupied. You could also do this with a stereo camera, for example, but we are using here range sensors just to simplify things a little bit more. And this joint belief, given sensor data and position information, can be broken up into this product of the probability that a certain cell is occupied or free, given the sensor data and given the pose information. So these guys here are binary random variables. This is not a binary random variable because it contains a large number of binary random variables. This is the whole map, this is an individual cell, and the individual cell is a binary random variable or represented with a binary random variable. And it is a binary random variable, that means we can use a technique to estimate the state of this variable. And this would be a base filter. So we could use a base filter to estimate the state of this binary random variable. And there's a variant of the base filter, the binary base filter, which is optimized for estimating the probability of a binary random variable. And we will use the second assumption in the derivation that I will show in a second, that we assume the state is static. That means the state doesn't change over time. So something which is once free will stay free, something which is once occupied will stay occupied. This is the assumption. That's an assumption that we will be using in here, that we don't model, for example, that the state of the system may change over time. So we are looking into the occupancy grid map now, and will now derive, starting from this term, a formula or an update rule, how we can estimate this probability given the sensor data and given the positional information. And again, we will use the mathematical tools that we have learned in one of the previous lectures in order to manipulate my probability distributions and derive an update rule for these type of map representations. And that's what we're diving in now. So we start deriving the static state binary base filter now. And we start with exactly the belief about the individual cell that I have shown before, and this is just kind of the product of those cells gives me the probability of the map. So it's totally fine for this derivation to just look into an individual cell. So we're just looking into one single grid cell right now. The first thing that we're going to do, we are applying Bayes' rule. So we use this equation and apply Bayes' rule. And we are, again, similar to the derivation of the base filter in the last lecture, we are swapping the variable zt, the last observation, with the variable we want to estimate. This time it's not x, it's not a localization problem, it is my mi, so the state of a cell. So I'm swapping mi and zt, so I need to swap them around. This happens what here. Mi and zt are swapped compared to here. And then we have the two additional terms, the prior and the evidence, that results from a direct application of Bayes' rule using background knowledge. So we have here P of zt, the likelihood of the current observation, given the state of that cell, the old observations, the old positional information, times the probability that the cell is occupied or free, given the same data except the last observation. And down here we have the probability of the current observation given all the past observation and the position information, but no map information being over here. Okay, So I can do the next update rule and exploit the Markov assumption. Again, the Markov assumption is something which says if I know the state of the world at a given point in time, then what happened in the past is independent from what happened in the future. Something we also exploited in the derivation of the general base filter in the last lecture. So that means all the old positional information, all the old pose information, doesn't matter if I want to estimate what I'm going to, or estimate the likelihood of my observation, given I know the state of the world. So I can drop here all the old observations and all the old pose information. I only need to keep the current pose because I need to know where the current scan is taken. So this is something that I need to know about the state of the world. So this equation simplifies here to P of ZT given MI and XT. And we can do something similar in here by saying in order to estimate if a state is occupied or free, we are not interested in the future position information. This is similar to the independence assumption that we also used in the derivation of the base filter by saying that wherever I am in the future, without any sensor information, doesn't help me to estimate if a state is occupied, a cell is occupied or free. The only exception might be if I'm actually standing in that cell. Then I could say, okay, this should be free because I'm standing here with my camera or with my laser range scanner or with my robot. But again, this is kind of an independence assumption that we are dropping here, or assuming here. So we drop this future position and just ignore xt over here. And then we want to further simplify this expression over here by using the first term again and apply again base rule, basically swapping that back after having exploited this independence assumption, after exploiting the Markov assumption. So we exploited the Markov assumption and then apply base rule for the first term again. And again, now swapping zt and mi. So zt and mi are again swapped. So you can see here, this is the application of base rule for this term. So we take this equation over here and put it in here. And then we have this term consisting now of 5 elements. So I could, by using the Markov assumption and the independence assumption, I could turn this equation over here in this equation. So we have the probability of a cell being occupied given the current observation and the current pose times the probability that of an observation given the position information but not containing any map information. So it's something that's probably tricky to estimate. So what's the probability of observing something, given I know where I am, but I have no idea what the world looks like? Probably tricky to estimate. And then we have the probability of the cell being occupied or free, given all the old information. So it's very similar to this recursive recursive term that we had seen before in the recursive base filter. And then we have down here the probability of a cell being occupied, given I know where I am, without any sensor information. Also probably something which may be tricky to estimate. Or maybe the position information doesn't really help me, at least in general. And then I have P of zt, the probability of an observation given the past observation and the past position information. And again, that's something which is probably tricky to estimate because we don't have a map and we have no idea where we are. So we have a sequence of observations taken at different points in time. I can start estimating a map from that, but then I have no idea where this observation has been taken. So this is a term which is probably hard to estimate. But what we can do is first, using an independence assumption for this term over here, what I just mentioned briefly, we can say the probability of a cell being occupied, given I know where the robot is, but I have no idea what the robot sees or senses, doesn't really help me unless the robot is standing in that cell. But there's something, let's ignore this. So we can drop xt over here and this just turns into the probability of a cell being occupied or free in general. And this is basically just the statistics about if I look to an environment or my assumption about the environment, do I have more free cells than occupied cells? This is basically what this prior encodes, what the average, if I just draw a random cell, how likely is the cell to be occupied or free? This kind of map prior, so to say, that we have. Okay, so I have now my simplified equation over here, but I still have a few terms which are hard for me to estimate. Something which may be tricky. What I haven't exploited so far is the fact that it's a binary random variable. That this variable just has 2 states, so just occupied or free. There are just 2 possibilities over here. And I can exploit that now by doing exactly the same derivation for the opposite event. So for the cell not being occupied, but the probability for the cell being free. So we'll get exactly the same derivation over here, except wherever there's an mi, there will be the negated event, so not mi. And the rest will stay exactly the same. So just by doing the same thing for the opposite event, p of not mi, given the same observations, I end up with exactly the same equation with the one I had here, except that every mi is replaced by not mi. Okay, so it's just kind of the event and the opposite event. And now I'm doing a trick which I can do, and this trick makes sense because I have a binary-based filter. So I have two possibilities in which the state can be in. So I'm computing the ratio of these two probabilities. So the probability of the event divided by the probability of the opposite event. And again, this is because I have two random variables, I covered all the possibilities, I kind of encoded in this ratio. So I'm computing the ratio of the probability of cell being occupied divided by the probability of that cell being free, estimated from sensor data. And kind of can write those two equations over here, divide them by each other. And the attractive thing is now that there are all the terms which are independent from mi or not mi, so that this doesn't pop up, are identical in both terms. And so they can be eliminated in this ratio. So for example, this term p of zt given xt pops up in both situations. Also this p of zt, or the likelihood of the current observation given all the previous observations and the pose information, is something which pops up in both situations and thus can be eliminated. So this goes away, and these two terms goes away because they pop up in both equations, and so they can actually be ignored. So then this ratio simplifies by just having these three terms which survive. What I can do is again just regroup those terms. So I'm writing the event and the opposite event for all those equations on top of each other. And since it's a product, I can separate this into three different products. So a product number 1, a product number 2, and a product number 3. And so the first term is the term that uses the current observation. So these terms over here are all the equations which contain the current observation, zt, so what our robot is seeing right now. The second term is a recursive term, so it's related to the state estimate of that same cell, but using only the old data up to the time t-1. And this is kind of the related to the recursive term that I had. It's just a ratio of these two recursive terms. And the last term over here is just prior information. What can I say about my map without having seen anything, without having been there? So what is my assumption about occupancy in this world, so to say? Okay, so what I have the ratio of the cell being occupied divided by the cell being free, given all the data. It can reduce this to a product of three terms, one related to the current observation, one related to a recursive term, and one related to prior information. And what I will do now, I will just introduce a new term, a new abbreviation, a new function that will allow me to simplify this expression over here. In theory, I can still use this term over here and do recursive state estimation with it, but I so far haven't recovered the original probability that I want to have. And this is something which is called the odds ratio, odds notational odds ratio. So the odds of x means p of x divided by 1 minus p of x. And you know this is exactly what we had before. It's the event divided by the opposite event. And this is something which we refer to as odds of x. So what I can do is I can multiply this equation with 1 minus p of x. And so this is multiplied on that side. If I swap the sides, I've written here p of x is odds x minus odds x times p of x. So what I then can do is I can take out this, can take this one, add it to the other side, and then what remains is p of x. Of course, it occurs in both things, so I can take it out of the equation. 1 plus odds of x equals odds of x. And then I can divide through this term over here. Divide by 1 plus odds of x. So this goes down here. So p of x is odds of x divided by 1 plus odds of x. Okay, so that's interesting, because what it allows me to do is it allows me to, given I have the odds, and the odds is something that I actually computed before, turn that back into the probability with this simple equation, odds divided by 1 plus odds. Or I can also write in the way as a 1 divided by 1 plus 1 divided by odds of x. So this is equivalent. So what I have in the end, I have an equation to turn those odds back into probabilities and also the probabilities into odds. So both sides of this term are there. So with those two equations, I can turn odds into probabilities and probabilities into odds. That's great, because what I've done before, I actually estimated those odds, right? So I have a rule to estimate those odds, and now I can use those these equations in order to turn the odds back into the original probabilities that I had. So just by using this equation down here and using the rule that I had before, I will end up in this update rule, that the probability that I wanted to estimate about the state of a cell, given all the observations and all the control commands, can be written down in this form over here, which is the ratio of those probabilities that I had, and then everything 1 divided by 1 plus this term over here, because there's a minus 1 over here. Okay? So with this rule, I can use those ratios that I can compute, or that I need to specify or can compute, depending on which term I'm referring to, and can turn this into the occupancy probability and can estimate the current state of every grid cell given my sensor observation and given my control commands. So for efficiency reasons, I can, however, take that a step further and use a slightly different form of this odds notation. They're called log odds notation, where I compute the logarithm of those odds, because as we will see in a second, this can substantially simplify the mathematical operations I need to do. Even those are kind of not too complicated, but we can make them even easier so that this occupancy grid update gets super fast. This was more important at the time when this algorithm was developed, which was in the early 1980s, but you can still use this today in order to very efficiently update your maps. So let's have a look how that works. So if again we go to this ratio, and we have here an odds term, here an odds term, here an odds term, and there an inverse odds term. And of course we could write it now as, for example, this term as odds of mi given zt and xt. And if we now go into this odds space first and then compute the logarithm of both terms, the logarithm on that side and the logarithm of that side. So just take the logarithm of both sides. I will refer to this as L of the variable, which is the log of the odds, therefore also called log odds. And the advantage of this is, first, the log odds, I have this ratio already encoded in here, and taking the logarithm of this turns this product into a sum. So basically I just have 3 sums that I need to execute, which makes this algorithm so fast. So L of x is nothing else than log of the odds, and by just taking the exponential of this odds, I can of course revert it back to the original probabilities. So I can go to this log odds space and can go back to the probability space, given these 2 equations. And if I do so, then I can write down the log odds of this term I'm interested in. It's the log odds of mi given zt and xt plus the log odds of the recursive term and the log odds of the prior. And just have the plus and minus over here depending if it was which part of the ratio it was. If it was the inverse or not. So in the end, what I need to do, I have my current estimate in my grid cell that I need to store. And this is the sum of 3 terms. The recursive term, so the old state of that cell before, the inverse sensor model, of the log odds of the inverse sensor model, so what the current sensor information provides me, minus the log of the prior. So in very short, this is kind of the new state of a cell at time t, so cell I at time t, LTI, so this refers to, is my inverse sensor model, so something which depends on what I'm seeing right now, plus the old value that it had, so it's just the value at the previous point in time, minus my prior information. So what I need to do if I have a new observation, I just need to iterate over all cells and update every cell with this single equation. So just need to add a value and subtract the value from the current value that I have. So basically I have a 2D array where I need to store the values, these log odds values for every cell, one number, one floating point operation, or one double number. And I just need to add something and subtract something from that cell. And this is an operation which can be done very, very fast, can even be parallelized in an easy fashion. So if we put this into an algorithmic form, you can see the occupancy grid map algorithm says, okay, I'm iterating over all cells, and then I'm checking if the cell is in the field of view of the sensor, so does the sensor see this cell at all? And if it sees the cell and can tell something about the occupancy, then I'm doing my cell update, and this is, again, just adding and subtracting a value. If not, I kind of keep the value it is, so if I do that in an array, I don't need to do any update over here, and that's it, and I return my two-dimensional array. So something which is very, very easy to do, very easy to implement, very fast to be done. And I can even parallelize this. So for example, summing over all cells, I can easily break down my map into small chunks and then operate this, perform this operation on different CPUs, on different threads, just updating a part of the map. So something which can be easily parallelized because there is no access to kind of the same data structure, at least in writing fashion, when I perform and parallelize this. So something which can be done very, very fast, very efficiently. And a few words about the history. This is an algorithm which has been developed by Moravec and Elfes in the beginning or the mid-80s. So it's an algorithm which is around in the robotics community since quite a while. And they used it for sonar sensors and to build occupancy grid maps with sonar sensors, having a robot which knows its pose, so was driving around through the environment, building a map, given known poses, estimating which part of the environment is occupied or free. And therefore it's also often referred to as mapping with known poses, because one of the first algorithms breaking up the space into occupied and free areas given known pose information, but have a probabilistic way for integrating sensor information. And so this was the core algorithm per se. We now, if we want to implement this on our real robot, we need to specify what is our inverse sensor model. And that, as the name says, depends on my sensor. So depending on how the sensor looks like, I end up having a different inverse sensor model that I need to specify for my sensor. And I want to do now is provide you two examples on how such a model could look like. So we start with the laser scanner example. So the laser scanners are typically rather precise sensors, especially if you talk here about, let's say, grid resolution of 5 by 5 centimeters or maybe 3 by 3 centimeters to environment in a rather fine-grained fashion, which is typically totally sufficient for doing indoor navigation, for example. Then the sensor is typically more accurate than this grid resolution. And so if we get a measurement, like a laser range measurement, where the noise is typically smaller than the grid resolution, we can say, okay, assuming that it's not an outlier at least, then we can say this cell where the beam ends is a cell where there's an object in there, and this cell is occupied. And all the cells where the ray passed over those cells are cells which are more likely to be free than occupied. And given that those sensors, laser scanners are rather precise, there's not that much noise involved in this process. So how does now an inverse sensor model actually looks like? So we are looking here into a deviation from the prior. So is it more likely to be occupied or more likely to be free with respect to my prior information? So what we have here is the range reading, what the sensor sees, sits over here at ZT. So this sits here in the middle. So this is the sensor reading that the sensor reports. And what this graph shows us is how we update the occupancy based on the sensor reading. So, and this is a distance from the sensor, which sits over here, up to the cell where the beam ends up, the distance where it ends up. So whatever lies before the return of the endpoint, so everything which is in here, sits in front of the sensor and didn't cause a reflection. So this is free space. So whatever is in between the sensor and the obstacle is free space, right? Because the sensor ray passed through those cells. And so their occupancy probably should be removed because they're now more likely to be free than being occupied. And this is something that I'm exploiting in here. Then at that cell where the beam ends, the probability that it is occupied is larger because there's an object or something which reflected that laser beam. So the occupancy probability will be increased. So it's more likely to be occupied than it is free. And whatever sits behind that cell is unknown. I don't know. I don't know how thick the walls are, or I don't know what's behind the wall. I can't look behind the wall. So I kind of keep with my prior information. I have no update to be done in here. So whatever is in front of this is kind of the free space. Whatever is here is the occupied space, and whatever is there, I have no idea what it is, no information about it. And so this is the inverse model that we use for laser rangefinders for performing this occupancy grid mapping. If we go for a sonar sensor, the situation changes a little bit. For an inverse sensor model of a sonar, I don't have just kind of one ray, like the laser ray. I have actually a cone of the sonar signal that is emitted. And then some object in this cone leads to a reflection. So the inverse sensor model for a sonar may look like this. So it's basically this cone structure which goes up and opens up in here. And then I got a reflection or return of the signal at some point over here. So those cells are more likely to be occupied, and those cells are more likely to be freed. Because if there wasn't been an obstacle somewhere in between, somewhere in here, I should have had a return already beforehand. Okay? So this is kind of the sensor cone, the whole cone that needs to be updated. For reasons of simplicity, I'm just looking here into this kind of ray, so in the plot that is very similar to the plot for the laser scanner that you've seen before, so that would be a good illustration for a laser scanner. So this red line is the x-axis of the plot, which now follows. And of course, I can put this axis going here through those individual cells, not just directly through those grid cells. And the inverse sensor model for the sonar sensors looks similar, but not identical. So we still have the same idea that we have somewhere over here, everything which sits in front of the measured distance is free space. So whatever sits here is my free space. So because I'm in front of the obstacle, if there would be an obstacle closer to the robot, I should have had a measured distance which is shorter. The return should have happened earlier. Then I have my measured distance Z over here, where I actually got the return signal from which the measured signal was. So, but this sensor is very noisy, and it may lead to reflections which are generate signals which are either closer to me or further away from me. So I'm here not as certain anymore, close to the object, where the return actually happens. So it's not this kind of step function for the laser scanner, it's kind of a smoother function going up, here just represented by a set of linear functions, taking values from smaller to larger values. Until I have a certain peak over here, if I'm kind of deep enough inside the obstacle, I said, okay, this is now an obstacle. So this area here represents basically the typical noise that my sensor has, which is, in this case, typically larger than the grid resolution that we are using. And then at some point in time, it will drop down again. So this is kind of the free space over here. This is again the occupied space, and the information down here is again no information that is actually provided because I can't look behind an object. And again, kind of how thick, how many cells I'm updating here is basically a prior information, an assumption about how thick my walls are. And I need to have a certain thickness over here because the sensor is so noisy. If I just have very, very thin walls, the number of times I'm actually reducing occupancy probability would typically override the points in time where I'm seeing an occupied obstacle. And therefore, I have to generate a certain thickness over here. So how does it look in reality? So this is a plot of different sonar range scans taking with the B21R robot. This was actually work that I have done in my very, very early years when I was starting a PhD. So you have, let's say, a map that you had built so far. You see the robot over here, the dark cells and the bright cells. And these are different sensor readings that you get from your sonar. And the sonar basically fires different sonars at the same point in time and generates these updates for this occupancy grid map. And you're basically integrating all those updates with the update rules that I have been showing in order to extend the maps. You can see here, this was the map before, then you get this set of observations, and then you can see how your map gets updated. And if you drive through the environment for an extended period of time and take your sensor data, then you can actually see here how a map looks like. So you have this ring of sonar sensors over here with 24 sonars firing at different points in time while you're traversing through the environment. And then you can actually, if you have good pose information, build a map which looks like this occupancy grid map. You can see here some areas are more grayish. This is a result that the robot wasn't certain, hasn't seen this space only for a few times. Also here, the reflections were a bit tricky. Also over here you can see this were actually glass panes which led to reflections, and they can see that some obstacles are generated actually behind the real obstacle. This is just caused due to the problems that the sonar sensor has when observing the environment. Then we can actually turn this map and return the maximum likelihood map. So what are the cells which are the cells more likely to be occupied or more likely to be free, which would then return this type of map representation over here, where we just put the values to 0 and 1 based on what we get from this sonar reading. So you can use this even with very old sensing technology and even sonars which don't provide very accurate results often and have some issues such as reflections, crosstalk and all these things. But if you integrate multiple observations into a map representation, you actually get decent or surprisingly good maps out of this sensor information. Today we will most of the time use this with laser range scanners, so with this kind of step function model that I've presented in the beginning, so that if you have sensor readings looking like this, so these are kind of just the endpoints plotted, you can actually even see here that there are some sprinkles around. These were actually a person walking through those corridors while recording the data, so violating the static world assumption. But if you turn this into an occupancy grid map, you can actually see that those moving objects are often removed in this map because the person is moving through the environment, the robot gets multiple observations, so it sees a space once or twice as occupied and afterwards as free again. And if you see it more often as free as occupied, you basically attribute this fact to your sensor noise rather than this static world. But if a person would be there and was standing for the majority of time, then just moving away once, the robot sees the cell as more often to be occupied rather than free, then of course the cell would stay occupied. So it's just kind of an effect that the static world assumption is not too bad for, let's say, quickly moving obstacles, but in general we haven't addressed that topic of dynamic objects at all in this representation, and actually not taking it into account in the mathematical model. So if you want to implement this yourself, one thing you need to do is you need to estimate which cells are actually covered by a range reading. And this is something which you can do if you think about drawing a line in an image. So let's say you want to draw a line from here to here in an image. Which cells should you actually color in order to draw that line? And this is an algorithm which stemmed from computer graphics, which is much older than the occupancy grid map algorithm, which is Bresenham's line algorithm. So if you want to estimate which cells are affected by a range reading by a laser scanner, for example, then you typically use Bresenham's line algorithm, which you provide this coordinate and this coordinate. It would tell you the number of the grid cells, the coordinates of the grid cells, which are affected by this line or which is crossed by this line. Then you would need to check those cells for occupancy or update those cells. It's a rather straightforward algorithm which just basically estimates always which part of this grid cell is intersected by the line and then moves to the left, right, bottom, and so on. And you basically get a list of your cells that are being updated. So if you want to implement this, look for Bresenham's line algorithm if you want to do this on your own. This is an example of an occupancy grid map built with a laser scanner from a larger indoor environment. This is the CSAIL building at MIT, where you can we're driving around with the robot, recording laser range information in 2D and then building a map of the environment. You can very nicely see occupied and unoccupied space. You can clearly see the walls. You can see some areas here where desks were standing, where it's a bit more cluttered. But overall, you can see the building structure quite nicely, and also brought you a short video how you can actually do this online. So while the robot is moving through the environment and kind of explores the space, we can update the map and integrate this information into the mapping process online. So we're performing this recursive map updates at every time we get a new sensor observation, and then we can build a map of the environment using this information. This is kind of a standard approach, how from a robot moving through the environment, assuming we know the trajectory and taking the sensor data into account, we can build a model of the environment. And this basically brings me to the end of the chapter today as an introduction into occupancy grid mapping, which is a popular technique for building maps of the environment. So we have looked here only in 2D, where the basic occupancy grid map algorithm was formulated in the 1980s by Moravec and Alphys. And their key idea was to discretize the world into independent cells. So the space is discretized into, with a uniform grid into cells, and every cell represents a small part of the space. And each cell can be either occupied or free. So we can use a binary random variable to estimate if this part of the environment is free or occupied. And we were doing this with a model that assumes independence between cells. So we assume the cell is either occupied or free. There have been extensions of occupancy grid maps which try to relax this assumption and take neighboring information into account, but then the underlying estimation algorithms become more complicated. We cannot use these simple, easy update rules that we have derived over here. The occupancy grid mapping algorithm in its original form also assumes a static world assumption. So it assumes the world is static, doesn't change. That means a cell is either occupied or it is free. And if it's occupied, it will stay occupied. If it's free, it will stay free. Again, an assumption which doesn't hold in general, or in most situations doesn't hold in the real world, but an assumption that the mapping algorithm does. And as a result of those three assumptions that I just said, which are the three key assumptions which are involved in here, we use a static state binary-based filter for every cell to update this. Why are all the three assumptions in there? It's a static state, so the world is static. It's a binary-based filter, so it estimates a binary random variable, and we do that per cell individually. That means the cells are independent of each other because we just compute the product of the joint of those updates we have computed, given the formula that we have presented here. So it's mapping with known poses. Mapping with known poses is relatively easy. We could easily write that down over here, and so far we assume to have known poses. Of course, the situation changes if your poses are unknown, because then the uncertainty of the pose information adds an uncertainty to which cells you should update. And then the whole system becomes much more complicated. And this is then something we refer to as simultaneous localization in mapping. So localize the robot and at the same time build a map of the environment. But for today, for now, we assume we have pose information. What we then have done, if we looked into this log odds notation, I used the log odds representation for every grid cell just because it's so fast to compute, because then everything just turns into computing sums over cells in a map, something that is very easy and can be done efficiently. I only have this inverse sensor model, but I just need to specify it once or pre-compute it, and then basically it's just taking values from lookup tables and adding them up, which is very, very efficiently realizable on modern computers as well as outdated computers which are 30 years or 40 years old by now. Another advantage of the occupancy grid map was that we don't need predefined features. We don't need to have a feature detector optimized to our sensor to estimate whatever, sift points from images or tree trunks from laser range data. So we are completely agnostic to this. The only thing we assume to know is that we get range information which tell me where the next obstacle is, so what's the distance to the closest obstacle in a certain direction. And this is the assumption that I assume to get from the scanner that I'm using over here. Again, we have done everything in 2D. We can also extend this to 3D using voxel grids. So just having a grid in the 3D world where every pixel turns into a cube, and just stack the cubes also in the Z directions. And then estimate the same random variable for the 3D world. I can directly employ that. The only thing I'm suffering if I do this in 3D typically is that the memory consumption grows substantially, and maybe I don't have enough memory to store larger maps, and so things may get a bit more complicated, and you can have optimized data structures such as octrees or octree inspired implementations, realizations in order to store your points, so you maybe don't want to avoid estimating the whole grid as a 3D array, but in theory the same what we've done in 2D can also be applied in 3D. So if you want to get further information about what I have presented here, again, recommend the Probabilistic Robotics book. The chapter 4.2 investigates the static state binary-based filter in a very similar way that I have done this here, and we've derived how we actually end up with this static state binary based filter by using the trick of computing the ratios of both probabilities. And then the occupancy grid mapping algorithm is also in the book, and which tells you how to update this, how we do this for the sonar reading, or how we do this for the laser range scanner, for example. With this, I'm coming to the end of this lecture, and I hope you have learned today how you can build a map, plan-like map of the environment. If you have a range scanner, you can treat all the cells individually and estimate for every cell if it's more likely to be occupied or free, which then turns into a probabilistic representation, if you do this in a correct way, telling the probability that a cell is occupied or that it is free. In order to get probabilities out, of course, you have to specify your sensor model and have to estimate what is the probability of a cell being occupied or being free if it's in front of the scanner. This can be a bit more tricky. You may need to calibrate your specific sensor so you get meaningful probability values out of this, but the mathematical framework for that is available, and you can do this estimation on your own and build maps of the environment, which will be also one of the homework assignments that we will give out for that course, that you need to build a map of the environment given pose information and laser range data and come up with a model of the environment. That's it from my side. Thank you very much for your attention, and I hope you enjoyed this lecture learning something about occupancy grid maps. Thank you very much.